toothpaste cap. I place it down, and I can look at the toothpaste cap. That's nothing new. That's what we've been talking about for the last few moments. But what if I looked into the mirror? What do I see and why? So, to understand that, let's put together what we've just been saying. One of them is the law of reflection, and the other one is, how do our eyes see something? How does our brain work, right? Remember the light travels in a straight line? And remember that to get an image, we need the two rays. We need some light going to our left eye and some going to our right eye, and we trace it back. See, and so what would happen here is, because the law of reflection, the light that leaves the cap and hits the mirror here bounces that way and is irrelevant when it comes to me seeing the cap. Now, if somebody else was standing over here, that would be an important beam of light for them. They would be able to see the cap and the reflection in the mirror, but that's pointless to me. Same thing down here. The light that would leave the cap and hit this part of the mirror would bounce off and go in this sort of direction. Maybe I should have drawn a normal here and a normal here to show you that I'm using the law of reflection to figure out where the light is going to go once it reflects. And I would say it hits here and it reflects, and this doesn't go to my eyes. So as far as I'm concerned, this is a useless beam. Again, somebody else, this may be important, but not to me. So where and how would the light travel that would go to my eyes so I could see it? Okay, well, here's my eyes over here. Here's the mirror. Here's the cap. How could the light leave the cap, hit the mirror, go to my eyes, and still obey the law of reflection? And so if we put all that together, it would have to look something like this. The light would probably hit somewhere about here and go to one eye. And another beam would hit about here and go to my other eye. Those are the two important beams or rays that are important for me to see. Now, remember how my body sees an image, or my brain sees an image? Remember, my brain then thinks it travels in a straight line, right? I stand here and I say, why do I see an image of that pole right there? And I go, okay, I'm going to trace that ray back. I'm going to trace this ray back. And where those rays converge, that's where the pole is. That's how I get my binocular vision. That's why I decide how deep it is. And so coming up to this picture, I would do something like this. I would say, okay, I'm going to trace this back, and in my brain, and this is a terrible picture, so I'm going to try to draw a little better one here in just a second. Maybe I would say this is where the cap would appear to be for my brain. And so again, coming over here, and maybe I'll angle the make-believe cap up at an angle. In fact, maybe because it's black, it doesn't stand out as much. Maybe I'll do something that's red. But maybe that's too tall. I don't know if you can kind of see the image in the camera. But if you then look at that, I could stand here and I could say, there is the object and there is the image. And when I say there is the image, notice I'm pointing in the mirror. I'm pointing behind the mirror. I'm saying it's back. It's not on the surface of the mirror. It's not like a painting or like a drawing or like a TV screen or even a movie screen where I can say, well, there it is. It's right on the screen. No. This, my brain is saying, this is actually back inside of it. And that's what I'm trying to show you with this poorly drawn rays. And I'm going to do better so I can do some geometry. But my brain would tell me there back here is an image. And it is the image of this object. And so we'll call the object the real thing, where the light actually comes from. But as it bounces off in the mirror, as it bounces off and goes to my eyes, it can trick my eyes, if you will. I could think it's somewhere behind it. Now, I say trick with a little bit of air quotes because most of us, I don't think, are tricked. I mean, most of us come over here and we don't look at this red box and go, hey, check it out. There's 2 red boxes over here. I'll take this one and... well, I'll grab that one first. No, we don't do that. We know it's an image, but I want to convince you, your eyes really think it's really one and the same. In fact, I always find it very entertaining when in the movies, the camera people love to do this. I was thinking of one movie I was watching. You know, they went on a commercial break, and then they came back after the commercial. You were looking not quite face on, but to the side of a woman brushing her hair. And then the camera pulls back. And as it pulls back far enough, you realize, oh, that wasn't the woman. The woman's here. You're actually seeing the back of the woman. You're seeing the woman with the reflection in the mirror. But boy, when the camera zoomed in and only had the image, you could not tell that. It's not until you saw the whole picture. So when I say trick, humans' brains are smarter than that. But my mom's little dog is a good example of not being very smart, because every time I put that little dog out, you know, go see my mom and say, okay, hey, your dog, I'm going to let your dog out, so I can go to the bathroom. And so I open the slider and let the dog out and close it. The dog goes to the bathroom, and then the dog comes back to the slider, and the first thing the dog sees is another dog in their house. Now, of course, it's just the reflection of the dog in the slider window. But the dog gets all mad and starts barking and yelping and snapping at this other dog. And it's obnoxious. And it's like, look, don't worry about that dog. And I try to go around the outside and show, look, it's a reflection. And the dog doesn't get it. It just doesn't realize it is a reflection. But you, being smarter, probably don't confuse yourself. But I'm trying to use that story to convince you that the physics is a lot the same. In fact, identically the same. And so the light coming from that reflection really will look like the light coming from an image, from an object. So that's why we call it an image. So that our discussion we can distinguish between which is the object and which is the image as the light reflects off. Now, here let's get into some geometry. We'll start with some simple geometry. But again, coming back to this red object here, so this is the object, and as the light bounces off and it comes to me, and so this is the image, I would say it is actually behind the mirror. If I didn't know it was an image, I might be tempted to reach around and grab it because it is inside. It has a depth perception to it. And I guess my question for you would be, well, then how far deep is that object? I'm sorry, the image from the object. How deep is it inside the mirror? Or how big is it? Is the image bigger, smaller, the same size? And we can answer that with the law of reflection, knowing that light travels in straight lines, knowing that it has to go to our eyes, knowing that we have to have binocular vision, and a little geometry. If we put all those together, we can answer, what does this image really look like in our eyes? So let me give it a shot here. So let me start here with the mirror again. Let me try to draw a little bit nicer picture. Here, I'll just make a dot here at the beginning, will be my object. And over here somewhere, and it's really not important, as you'll see, where the person stands, but this will be my observer. Actually, maybe I'd be better not to actually specify the observer, because if I draw one ray that hits the mirror and bounces off, okay, straight lines, and note that the incident angle is equal to the reflected angle. Okay, so those two angles are equal. There's the law of reflection. I could say, as I get ready to do my question about, okay, where is the image, I would say, okay, this is one ray. Let's say that's the ray that goes to my right eye. So how about the other ray, my left eye? So let me draw another one. a little bit closer in for my right eye. Just to make my math a little bit easier, I'm going to draw this one. Here's the cap. What happens to the ray that goes straight in? Now, when I say straight in, that would be an angle of 0 from the normal. So it would bounce and go straight back out. And so to help me kind of do my geometry here and to figure out where a person standing over here, looking at the light that bounces off the mirror, where your brain would say the image is, your brain would do this. Your brain would trace this ray back and say this ray appears to be coming somewhere back here. And I'm going to put a dotted line because the light didn't really come from back there. That's kind of what my brain would associate. Remember, my brain thinks the light travels in a straight line. And it does. That's what I'm used to. That's what my brain is programmed that way. That's why I wanted to show you light travels in a straight line. I've learned since a little kid to figure out that, hey, if I look over there and there's a door and I look over there, there's a fire extinguisher, the light came straight to me. If there's a fire, I go that way for the fire extinguisher. That's where I know it is. Sound waves don't always do that. Sound waves can bend around corners. I know that if I were to stand here and hear somebody talk, and of course our door's not open at the moment, but if the door was open, it doesn't mean that I can just look out and see them just because I heard them. They could be around the corner and they talk and the sound waves bending around and they come in like this. They what we call diffract. And so I would say that just because I hear them doesn't mean I can see them. The light goes in a straight line. The sound waves do not. And so I can't just hear something and go, oh, there it is. When I hear something, I got to go, oh, where did that come from? And so it's a little more complicated. Anyways, that's why I'm going to draw this ray. So I'm going to draw this back here and say this is where the light came from, or at least appears to come from for my observer. And then the same thing here. I'm going to say this is where the light appears to come from. So if this is the ray that goes into my left eye, and this is the one that goes, or left eye, right eye, and I trace them back in my brain. Now, I'll say in my brain, because they didn't really come from here. Right here where they cross would be where my brain is saying, where is that image? And so I'll say it again, this is a much better drawing than the one I had before, but notice that this is saying that the image, and so let me just put image here and object here. This is saying that that image is inside of the mirror. That's why, again, if I were to look at this and I would look at the image, and if I really wanted to grab the image, I wouldn't reach and touch the mirror. I would be trying to go past the mirror. And if I didn't realize it, I would actually hit the mirror. Or if I thought it was a mirror, but maybe thought it was a window, I would reach around and go, oh, there it is, and I'd grab it. But there's nothing there. It just appears to be coming from there. And so one of my questions I had for you was this. Where does that image appear to be? How far back behind the mirror is that image? Let's give it a symbol. Let's call it d sub I for distance of the image. And let me pause and point out, notice I am measuring distance from the mirror. So it's from the mirror to the image. And since I'm going to do some geometry, you could imagine there's a connection between where is the image and where is the object. So let me put a d sub O for the distance of the object. The object, again, measured from the mirror. So all of our distance are measured from the mirror, not from each other. So it's not from object to image. It's from the object distance is from object to mirror, and image distance is from mirror to image. But here's my first question. What is that image distance? And so here's our first bit of geometry. Not real hard geometry yet, but nonetheless, some good geometry. If I were to take this green marker and make a triangle right here, and this blue marker and make a blue triangle. And I would dig back into my mathematics and say, okay, let's look at these triangles. Can I prove anything about these triangles? And I claim from the law of reflection the answer is yes. So watch this. Remember, from the law of reflection, we already said these two angles were equal. So let me draw the normal on back. Because one of the things from geometry, they're called vertical angles, is if you take a line and another line and they cross, the angle on this side is equal to the angle on the other side, right? That's a vertical angle. So if this is the incident angle and this is the reflected angle is equal to the incident because of the law of reflection. Now, with that in mind, then the geometry says because of the vertical angles, it would be equal to that. Now, let's look at this angle. Again, I'm going to have to go back to some geometry here. But remember, this is a normal. And remember, this was set up so that it went straight in and bounced back. So this is a normal. So these two are parallel. And so if you have two lines that are parallel, and then you cross it, then what we call alternate interior angles, here and here, are equal. And so two angles that are crossed by a transit, the alternate interior angles are equal. So I'm going to say that this angle is the same as that angle, which is the same as that angle, which is the same as that angle. And then I will also use alternate interior angles to say this, that these are parallel lines, and in the green triangle, that angle would be equal to that angle. So as I look at these two triangles, I have just proven that those two angles are the same. And in fact, these are each right angles, so those two are equals or the same. Now again, trying to remind you something from geometry, do you remember what the sum of all three angles in a triangle add up to? Yeah, it's 180 degrees. So if you have two angles that are already equal, then that means the third angles also have to be equal. So I would say at this point, using my geometry and my law of reflections on these straight lines, I have concluded that those two triangles, the green one and the blue one, have the same angles. Now, that doesn't mean they're the same size. I've still got another step to do if I want to prove that. Triangles that have the same angles means they have the same shape, but they can be bigger or smaller. So we call those similar triangles. But if they also have the same size, they're called congruent triangles. And I claim that these are also congruent because look where the triangles overlap. This vertical green is the same length as that vertical blue. And again, if you need to go back and dig up some of your geometry, we have these proofs of saying, how do you know that all the sides and all the angles of two triangles are equal? Those are called congruent triangles. And there's a couple of proofs. And one of them is called the Anglesideangle proof. That is, if you could show that a corresponding angle, then a corresponding side, then a corresponding angle are the same on those two triangles, then they are congruent. That means all three angles match and all three lengths match. And I would say that's what I have right now. And so using the Anglesideangle proof, I'm trying to say that the green one is congruent to the blue one. Now, I'll just repeat it again. What does congruent mean? Congruent means that all the angles are equal and all the sides. If just the angles, they would have the same shape, so they're similar. But if also all the sides match, they are congruent. And that leads me to my answer. Because now that I've shown they are congruent, this side must match that side. That means object distance is the same as image distance. And so there's what I was after. I was after this question: where is the image? And that was more of a formal proof to something that was probably pretty obvious to you. It was pretty obvious, maybe in the sense that you said, yeah, I've looked in a mirror before, I get the idea. I see that the image is not on the surface of the mirror, it is inside. I could even see that if I take one step towards the mirror, the image takes one step. If I take one step back, it takes one step back. So if we both started up against the mirror, we would be here, and if we took a step and two back, then my image would take two back. So most people don't find this too surprising to say, okay, yeah, your image is not on the surface, and your image is the same distance back in the mirror that you are, the object is in front of the mirror. And so again, not an overwhelming surprise, but I did want to go through the geometry here, because this does get a lot harder when the shape of the mirror changes. What if instead I have this mirror? And this mirror is bowed out. So we've got a lot to talk about this one, so I'll wait till we build up to it. But the chairs in this room could be your image. And so as you look into this mirror, you will see this empty classroom of all these chairs. And all these chairs then are not the same distance into the mirror as they are in front of the mirror. So where are they? Well, that's going to take some tougher geometry. Or even better is this mirror. This mirror is curved also, and it's curved the other way. And it's curved with a concave in. And so as you look at the mirrors, or the chairs in here, it might even get kind of fuzzy and hard to even focus with a camera, but your eyes could usually pick it out if it was face to face. And so something that's far away will be in this mirror, but it won't be as far away as the image as the object is. In fact, it won't even be right side up. The stuff that's far away, like that chair in the back of the room, if you get that chair in here, that chair is upside down. It's smaller and upside down. Whereas if I were to put something close to it, like one of these markers here, the image in this is right side up. It's right side up and bigger. And its distance is not the same as the object distance. So again, we've got some tougher geometry to do, but this is a good first step. And this is the part that I was saying, that I want to go a lot more into the geometry than your author did, because your author just says, oh, here's a curved mirror, figure out where the image is. And it's really some pretty advanced geometry, which it might have been a while since you've done your geometry. Well, let me keep going with this flat mirror, because I could extend this question to not only where is it, but how tall is the image? Watch. Let me come back here. Let me maybe add some little color here. I just made a little dot here. Had I made a line, and usually we like to make an arrowhead, because as you saw, sometimes the image gets inverted, and an arrowhead you can tell that. Now, what I'll tell you the answer here for a flat mirror is it never gets inverted. But as you just saw with that one curved mirror, the one that went inward, one we're going to call concave mirror, it can invert it. And so I'll just draw a little arrowhead, and I'll do this. I will say, let's say that the height of the object is h. Okay, h. So, where's the image? How tall is the image? Well, maybe to make the color code match, I'll stick to the red here. But you could say that what I've done in this previous conversation was really find out where the image of the top of the arrowhead is. I could do the same logic with the middle of the arrowhead. So if we treat the middle of the arrowhead as a point, we would go through, and as we already said, and I'll just point it out, that the object and image distances are the same, I would have to include that the middle of the arrowhead would be right here. And the top of the arrowhead would be right here. And the same logic would say the bottom of the arrowhead would be right here. And so what I would get is an arrowhead that the bottom would be straight across from the bottom of the object, and the top of the image of the arrowhead would be straight across from the top of the object of the top of the real object, which is the arrowhead. And so because of that, I would really just be saying something, what you might say very simple, that the image must be the same height as the object. And so I will put, let me do something better. Why don't I put an h sub o for the height of the object and an h sub I for the height of the image. And so I will have height of object and height of image. Yay! And that's really what I wanted to do with this first mirror, is to demonstrate using the law of reflection, also with the idea that we see something with our binocular vision, also that the light travels in a straight line. If I put all that together with geometry, I can answer this question: where is the image and how big is the image? And this is the part that I was saying, your author just leaves it at that and says, good luck. And says, go do your own geometry for the curved mirrors. But let me help you with the curved mirrors. Time-wise, I don't know how far we'll get, but whatever far we'll get, we'll definitely pick this up on Monday. Because again, the geometry is not quite so simple. The geometry we just did, I would not call it simple, but hopefully it was able to work off the rust that you might have from your geometry, and so that hopefully it makes sense, especially those words like similar triangles versus congruent triangles and alternate interior angles. And so I'm going to work with that a lot, and you're going to be required to work with that a lot. Okay, so before I leave the flat mirror, I wanted you to see something kind of special here. You might have already noticed it. I don't know if you did. If you did, great. If you didn't, maybe better still. Because besides this red object in front of the mirror, I have a little bench rod in front of the mirror. And it's pretty tall. Do you see how tall it goes up here? It is really, really tall. So if you are looking at the object, the light would come right here. But I'm hoping also that as you can see the reflection out of this mirror, you could also see the image. And so if you look down here, like at the base, you'll see that the image has the same base. And it's the same distance back in. But here's the neat thing. I don't know if you caught this, but the mirror only goes this high. The object is much higher. And so, I have placed in the back another post that the only part you can see when you've got a front view is this part that is above, because there's no mirror there. So if I turn this back around, and even if I change the angle here, I'm hoping that what it looks like is that the top part of this, which is a real object, and there's no reflection because there's no mirror up here, but down here in the bottom part, the reflection from here is really the reflection of this object. And they look continuous. This pole comes down and makes that. So the lower half, you're actually seeing the reflection of this one, and the upper half you're seeing here. And you are hopefully seeing that this object is actually back inside of the mirror. This is trying to convince you that the image is not on the surface of the mirror. The image is actually inside, deep inside of the mirror. And these two look the same. In fact, the best way to see it is when I actually move it. If I actually take this post and I move it, you will see it much better. That you got the bottom half of this image here, and then the top half is actually the second object that is behind it. And so that's why this setup is here, to really convince you that the image looks like an object, and it is back inside. And of course now we solved mathematically that at least for a flat mirror, the distance of the image is the same as the distance of the object, and the height of the image is the same as the height of the object. And those are the kind of questions you'll be asked on the homework and on the test. It'll say, where is the image? Where or how big is the image? Those are some very common questions. And in fact, before I leave the flat mirrors too much, your author does two more things here. Your author says what it would happen if you had two flat mirrors parallel to each other and you stood in the middle of them looking at some kind of object. Or what would happen if you had two flat mirrors that were mounted at 90 degrees? And you had some kind of object. Well, I'll start with the two parallel mirrors. This is always fun. Sometimes you see them a lot. I know at my dentist office they have this, where you enter a kind of a small waiting room, and they've got a mirror on one side and some chairs over here, and then about 10 feet on the other side there's another wall with some chairs and a mirror. And so as we're waiting, you can kind of look at whatever's in this small little room as you're in this small little room. And of course, whatever it is, you could see the object directly. And so let's say I'm sitting here and there's a table with some magazines on it. Although with the coronavirus, now they took the magazines out. I just got a letter from my dentist and said, okay, your appointment that was scheduled for July is postponed till August. Okay. And when you do come, you will notice some changes, and one of those is we've taken all the magazines and papers out, so nobody's handling, and you have to come with a mask anyway. So it's like, oh man. So I guess I'll bring my own book there. But they don't want people touching each stuff, so I get it. But anyways, in a normal setting, let's say this is a magazine. I can see the magazine, but I could also see this. I could also see the light that reflects, and so I would see an image of that magazine. But I could also see this. I could see a bounce off of here, and a bounce off of here, and a bounce off of here. And so as I look at this, I'm actually seeing, you'd say this first bounce is probably really represented with that image. And so what I'm seeing then is the reflection out of this mirror of that image. And so that's like way over here. Of course, I could also see this, a bounce and a bounce and a bounce and a bounce. And so I see another one. And this will get kind of busy, but there would be multiple bounces. And so as I'm stuck between these two parallel mirrors, I could see the one ricochet, the double ricochet, the triple ricochet, and I could see magazine after magazine after magazine after magazine after magazine. And this goes on indefinitely. Of course, the angles change and they begin to overlap each other. And so I know in mine, I've tried to count. I go, how many can we see? 1, 2, 3, 4, 5, 6. And I think I've gotten up to like 17, and you can just kind of see about 17 of them. And you could look the other way and do the same thing, and you see that the same ricochets in the other directions. Now, the corner reflectors I love, and in fact, it was just yesterday. No, it was 3 days ago. Just to relax a little bit. I like to read Quora. I don't know if you guys read Quora. The people write in questions, and experts are supposed to answer it. And sometimes people who answer them aren't experts, and so I get mixed signals. Sometimes I like it, sometimes I don't. I get some great information. But one person wrote in and said, during the Apollo missions, the astronauts left a mirror so that NASA could send up a laser beam and measure the distance to the mirror. How did they know the right angle to adjust the mirror? And I was like, oh, that's actually a really good question, but a simple answer. You see, what they did is they put what they call a corner reflector. It wasn't just one mirror, it was this shape. Because watch the light here. If the light comes in and hits the first mirror, it bounces off, hits the second mirror, and bounces off here. And these two beams are actually exactly parallel. We could go through a little geometry. And so if this is the incident angle, then this would be the incident angle, at least of the first one. And then it would come in and there would be a second incident angle. Let me call it theta 2, and it would reflect here. This would be a theta 2. So using the law of reflection, I would say these two angles are equal. And also using the law of reflection, I would say these two angles are equal. But I would also say those four angles right here, which is the bending of this whole beam, adds up to the 180 degrees. Watch. I think you can see it here. If I draw this across and take advantage that this is a right angle, then this right here would be a theta 2, and so these would be alternate interior angles, and this right here would be what I called theta initial. And since this triangle has to add up to 180 and this is already 90, these two must add up to 90. So what I'm saying is initial and theta 2 add up to 90. And so if you add up initial and initial twice, and then theta 2 and theta 2 twice, you would get 90 and 90, that's 180 degrees. And so this beam comes in and goes exactly back in the same direction. And notice, and you can see it with a different color, it wouldn't matter what angle this is. The light beam could have come in at this angle. It would have hit here and bounced off, and hit here and bounced off. And so this angle coming in would bounce off and go exactly back in the same direction. So, to answer that Cora question, and no, I didn't try to answer it.